Good afternoon, everyone, and thank you for joining us. We are BIM Avengers, Group 6 of the Global BIM Management Program of Session May 2024. Today, we are excited to present our final master project, a full-cycle BIM implementation for the Vizig building, a 9-story commercial office project located in Barcelona. To ensure a realistic and comprehensive learning experience, our goal was to simulate a complete life cycle using an ISO 19650 compliant framework under an integrated project delivery model. That's a collaborative approach where all stakeholders are involved early on to maximize efficiency. We structure ourselves into agile roles, allowing us to be flexible and responsive and rotate responsibilities across phases, planning and design, then construction and handover, giving us both continuity and valuable experience in managing phase transitions. Ultimately, this approach tested and sufficiently enhanced our coordination, planning, and collaborative problem-solving skills essential for success in any construction project.
We would like to start by briefly presenting the agenda for today's presentation. First, we will provide an overview of the project's brief and the initial framework that shaped our methodology. This will be followed by a breakdown of our BIM implementation structure, highlighting interoperability workflows and alignments with ISO 19650. We will then illustrate how we managed interdisciplinary coordination, applied digital tools during the construction phase, and structured the final digital handover. To close, we will reflect on the key lessons and insights gained over the course of the project. Let us begin with an overview of the project's brief and the initial framework. The Vizig building, with its cantilevered facade, was ideal for multidisciplinary coordination. We simulated the full life cycle from design to operation, with objectives that included ISO 19650 compliance, OpenBIM, and COBie delivery. Working under an IPD structure, we embraced shared risk, mutual accountability, and structured model sharing protocols from the outset. To ensure a structured and efficient workflow, we developed a level 1 process map. This high-level overview, based on the ISO 19650 lifecycle, defined the sequence of activities, key decision points, and information exchanges across all project stages. Complementing this, our BIM execution plan served as our central management document. It aligned critical project elements, including team roles, project phases, level of information need, and common data environment procedures. The BAP functioned as both our strategic planning framework and our practical coordination tool, guiding our BIM implementation throughout the project.
To establish a single source of truth for our project data, we used the common data environment. Catenda Hub served as our ISO 19650 compliant CDE, ensuring efficient information management. File access was managed through role-based permissions, with files progressing from work in progress to shared and finally to published. This controlled process, paired with strict naming conventions, metadata tagging, and BCF issue tracking, enabled traceability and centralized coordination throughout the project. To enable seamless interoperability, we established a comprehensive OpenBIM strategy built on 4 key pillars: tools, coordination, exchange, and federation. We used discipline-specific software, including Revit and ArchiCAD for architectural design and MEP modeling, and Tekla for structural engineering. IFC served as our standard format for data exchange, while BCF facilitated efficient issue tracking. To manage data requirements, we used the Building Smart Data Dictionary, or BSDD, to define structured data requirements within our model responsibility matrix. As for coordination, generating information delivery specifications, or IDS, to ensure alignment, consistency, and compliance with the EIR. As for coordination, we began with federated model reviews in Catenda Hub and then transitioned to Revisto for advanced model navigation and handover planning. For standardized information management, we applied ISO 19650 Part 1 for principles and terminology, Part 2 for structuring and delivery phase information, Part 4 for standardized exchange protocols, and Part 5 for secure and controlled data access. Part 3, while acknowledged, was outside the scope of this academic project. This framework was supported by our BEP, which included a RACI matrix, structured MIDP, ISO-based file naming, and classified information using Uniclass classification system. The CDE lifecycle states enabled progression from design to delivery with full control.
In the design phase, team developed discipline-specific models and coordinated them through structured IFC-based workflows. Clash reviews, model walkthroughs, and validation cycles were conducted during each sprint. Internal quality control was managed using tailored checklists, ensuring consistency and alignment before federation. Coordination was a primary BIM use. We managed issue tracking in Catenda using BCF from early design, then transitioned it to Revisto for integrated model reviews. And clash detection also we utilized Revisto. The traceability and the visual clarity of these tools enhanced model quality at each delivery milestones.
In pre-construction, we finalized coordination and used Synchro for 4D sequencing to simulate the construction timeline. We visualized phasing constraints, validated logics, and refined structural and service coordination, preparing the foundation of AIM development. During construction and handover, we applied BIM uses defined in our BEP, 5D cost estimation, record model development, COBI population, and AIM delivery. We extracted Celebi quantities to Excel and manage issues in Revisto. The AIM was complied from federated models with validated level of information needs metadata. COBI was populated from Revit and ArchiCAD, aligned through IFC workflows and structured to meet exchange information requirements. All deliverables were validated and published in Catenda Hub, forming a solid foundation for facility management and future digital twin use. Quality assurance was integrated across all phases, forming a continuous part of our modeling and coordination workflows. Each member performed internal reviews using Appendix 5.1, while cross-discipline coordination and verified with Appendix 5.2. We validated IFC structure and attribute completeness using Celebi, making a QA and ongoing and sprint integrated process.
We used Agile Scrum throughout, conducting sprint planning, stand-ups, and retrospectives. Role rotation ensured knowledge continuity across project phases. Handover between Group 1 and Group 2 was documented and aligned with our BEP, simulating real-world project transitions. We managed a complex multi-platform environment by establishing shared IFC workflows and harmonizing output across disciplines. Clear protocols, consistent data structures, and aligned coordination processes enabled us to maintain quality and reliability throughout. Team initiative, structured peer support, and continuous alignment ensured precise delivery across all project phases. We observed that well-structured data and clear communication consistently led to high-quality outputs. Adaptability across tools and roles enhanced our efficiency and delivery consistency. Above all, collaboration remained our strongest asset. Our results reflected not just technical competence, but a cohesive and agile team effort.
This project was more than a technical exercise. It was a coordinated lifecycle-driven delivery, shaped by collaboration and shared standards. We thank our mentor Rania and the ZIGURAT faculty for their guidance and for creating a program rooted in a real-world application. To our team, your professionalism and cohesion define the quality of this work. Thank you for your attention. We welcome your feedback and questions.